Now let's look in detail at the efficient spatial coding. When we looked at its gist using our intuition from stereo coding, we looked at only two spatial locations, x1 and x2. The spatial input signals are then input S at x1 and x2. Now we need to look at all spatial locations at x3, x4, x5, etc. And so now the input is a high-dimensional vector with as many components as the number of spatial locations. We again apply our recipe so that the efficient transform K is having three components: decorrelation, gain control, and multiplexing. We now show that for retinal spatial coding, decorrelation is a Fourier transform of the spatial image to its Fourier components. Gain control is to give a specific weight to each Fourier component according to its signal power in this component. And multiplexing is the inverse Fourier transform. The net transform is then taking such an input image and transform it to an encoded image. The pixel here represent the photoreceptor activities, pixel 1, 2, 3, 4, and so on. And the pixel here represent retinal ganglion cell activities, cell 1, 2, etc. And each of these retinal ganglion cell is a weighted sum of these input activities by this encoding transform. Now let's look at each of these three components of this transform in detail. First, decorrelation. To do this, we need to know the correlation matrix for correlations between each image pixel and another image pixel, okay, any other image pixel. So for n-dimensional input vector S for n pixels, this matrix Rs is then an n by n matrix. The first row is the correlation between the first pixel, x1, and every other pixel. And the first item, x1 is the self-correlation. And the second row is the second pixel, x2, with every other pixel. So of course at x1 it's signal S, x1, and so on, yeah? And so on and so forth. And the last row is the last image pixel. And the diagonal elements, you notice, these are the self-correlations between each pixel to itself. In natural images, the correlation between two pixels, okay, here depicts the correlation, they decay with the distance between the two pixels. So the self-correlation is the distance 0, that's the highest. This means all these self-correlation on the diagonal elements, they are all equal to each other, they are all the highest. And if you have an array of pixels, let's say x1, x2, x3, x4, 4, and 5, which can be, just array somewhere there, okay, 1, 2, 3, 4, 5 next to each other, then the correlation between pixel 1 and pixel 2 is the same as the correlation between pixel 2 and pixel 3 because the distance between them are the same, yeah, it's only depending on the distance, and also between 3 and 4 and so on. So that means this off-diagonal element, yeah, x1 and x2 is the same as x2, x3, and so on. So these off-diagonal elements, just one distance away from diagonal, they are all equal to each other. And similarly, if you look at the correlation between x1 and x3, it's the same as the correlation between x2 and x4 because again, they have the same distance, even though this is a longer distance, yeah. So therefore, the correlation value will be less. But nevertheless, that means these off-diagonal elements, okay, distance 2 away from diagonal, they are also all the same, equal to each other, and so on, yeah? So This means that this correlation matrix can be written like this. Okay, we take the self-correlation factor outside the matrix, and then the diagonal elements are all equal to 1 because this factor is then taken out. Yeah, and these off-diagonal elements are equal to R1, and R1 is basically the ratio between this off-diagonal element and the self-correlation, which is this one. Yeah, and similarly, you have this R2. Okay, you can see that R1 must be less than 1 because as the correlation decays with distance, so it must be less than 1, and R2 is probably should be less than R1, etc. Yeah, and so therefore, also another thing you notice is this is also R1 because it's symmetric. Yeah, you have correlation between x1 and x2 is equal to the correlation between x2 and x1, so therefore this is all symmetric. So therefore, within one row, and then next to this diagonal element, the left one is R1, the right one is R1, and so on. Each row is like that. Of course, when you come to the last row, the diagonal element is this one, and to the left one is R1, to the right one, it actually comes around. This is R1. And this is as if, the whole thing just can wrap around. This is called periodic boundary condition. Another way to look at it is as if, from pixel number 1, 2, 3, 4, it travels around the Earth and come back to its original first pixel from the other side. Yeah, it just means this is another way of saying, stating a mathematical formulation for an infinitely large input image. That means this input image is so large that it's much larger than this typical correlation distance where things are still correlated. To decorrelate, we transform this S vector by this decorrelation transform K0, so that the outcome is another n-dimensional vector, and each component of this vector is decorrelated from any other component.